Hey, we've got the energy and momentum packet. We're doing problem number 3. So, not that one, but hey, how about the one that says number 3? Took it apart because I don't have much room to work with right here, so let's take a look at this problem. It's got a ball bouncing off the wall. It says a ball of mass m is launched from a spring-loaded projectile launcher. The spring in the launcher has a spring constant k and is displaced by a distance of x from the equilibrium position before launching the ball. Assume the ball maintains only a constant horizontal velocity after its launch. So basically, it's like you got a gun and you shoot it out horizontally, but the thing doesn't drop due to gravity. The force F of the wall imparted on the ball is shown in the graph below as a function of time t. So you got this graph. First of all, we need to identify what kind of graph this is. This is a force by time graph. If you have a force applied for a time, there is an equation that works with that. A force times a change in time, or a force times time, is equal to a change in momentum, and so that might be something that's useful. So whenever you're working with a graph, just kind of know the variables that you're dealing with, and then that might give you a hint on the equations that you might have to use. Well, so let's see. It says derive expressions for the following in terms of these, and only these, and universal constants like gravity, or the acceleration due to gravity g. Let's see. Number 1, the work W done by the launcher on the ball. So we had a launcher, and it was like a spring-loaded launcher, right? Let's see, launched by a spring-loaded projectile launcher. So this thing is compressed, and what we know is that if a spring is compressed, then it's going to store some energy. It's going to store some potential energy. And so by the AP standard, we can say the potential energy stored by the spring. Now in my class, usually I'll do this. It's because for me, it's like we can actually know what we're talking about there. But anyways, so all this energy stored by the spring, the equation of energy stored by a spring is 1/2 kx squared, and so the k is the spring value of the spring, the Hooke's constant, and x is going to be how far you compress the spring or how far you stretch it from the equilibrium position. And the more you do that, the more energy you store. So the work done by the launcher on the ball, work is a force applied for a distance, and what force is the launcher putting on the ball? Well, it's going to be the spring force. And so we can think about it in terms of energy, because the amount of energy that the ball gets is equal to the potential energy of the spring. So here's the amount of energy that is in the spring, and that's going to be equal to the energy that the ball gets. How much energy does the ball start with? Well, it starts at rest in the launcher, and so all the energy that it gets is from that. So that should be equal to the work done on the ball, because that is a force applied for a certain distance. And I think that's it. We got, are we in the proper values? We have k, there's k. We have x, there's x. So I guess we can move on. So not that bad for that one. And so we go on to part 2. Part 2 says the velocity v of the ball out of the launcher. Now let's go back and think about energy again. Where did we get our energy from? It came from the potential energy of our spring. And where did it go to? It went into the ball. And what kind of energy is that? That's going to be energy of motion, or kinetic energy. So we start off with the potential energy of the spring, and we're giving that straight to the kinetic energy of the ball. All right, so what's the equation for potential energy of the spring? 1/2 kx squared, and then the kinetic energy of the ball is going to be 1/2 m of the ball. And we're using appropriate constants, so m, and then we have v, that's what we want, squared. So just keeping by the variables that we're working with. And I know some of you guys really don't like variables and you like to use numbers. Just think about the fact that numbers are actually variables that you've already assigned a value to. Okay, anyways, 1/2 goes away. We have k, we have x squared equals to mv squared. We're looking for v, so we're going to move the m over. Kx squared over m is equal to v squared. Get rid of the square, and that's what we get. So we get the square root of kx squared over m is equal to the velocity of the ball out of the launcher. Boom. Next part. We got the change in momentum of the ball. And so let's go back and think about what momentum is. Momentum is mv. And let's think about the momentum of the ball. Does a ball start with any momentum? Well, no. Does it get momentum? Yes. And, well, I guess the other question is, when are we talking about the change in momentum? Because not only are we talking about the ball coming out of the gun, but it also hits a wall, right? So I guess we could have been a little more specific. Um, are we talking about out of the gun? Is that the question? Because in that case, the change in momentum is just mv, pretty much that. It starts with 0 and it gets that much mv, and m is the mass of the ball, and v is actually that stuff. Okay. Um, and then let's see, I can put that into the square root. I can square it, so that would be m squared kx squared over m. And that's m kx squared over, well, I guess it's 1, right? So just square root of mkx squared. Um, well, I mean, is that what we're talking about? Is that's the mv out of the gun, right? That's a change in momentum there. But what happens when it hits the wall, right? That could be the other change in momentum. So as it hits the wall, is that the question that we're asking here? So that's the other thing we can look at. What's the change in momentum as it hits the wall? Well, the initial momentum that it has would be this much as it hit the wall, because that's the momentum that it had out of the gun. But when it hits this wall, it bounces back the other way. And we're actually given this. We're given this graph of force times by time, and we know that force by time is going to be impulse. So the answer to that question, that how much momentum change is given to the ball by the wall, that would essentially be the area underneath this curve, because force times time is really talking about the area of this shape. So the area of this shape, we have two triangles here, really. I don't want to just use one. We have one triangle here of 5t at the base, and then we have 5f as the height. So 5 times 5 is 25, divided by 2 is 12.5. 12.5 ft is going to be the area of this side. So 12.5 ft is the area of that side, and I guess by symmetry, this would be 12.5 ft on the other side. So the total area here is going to be 25 ft. So if we're talking about as it hits the wall, here is out of the gun. As it hits the wall, put a little star there, is going to be the area of that shape to the axes that it's resting on, 25f times t, and f and t are variables that we can use. So that could be equal to the change in momentum as it hits the wall. This one is the change in momentum from the gun. So two different things there. May talk about one, may talk about the other. Moving on, we got problem number 4, or part number 4. Use my other paper. It says the velocity v prime of the ball after it bounces off the wall. So let's see. The velocity v prime of the ball after it bounces off the wall. So it's a collision, so we probably need to use momentum. Let's talk about the initial momentum is equal to something, because that might help us find the final velocity if we know the final momentum. The initial momentum is going to be mv. And if you remember, we just figured out the v out of the gun. That's in part 2. So this is actually m square root kx squared over m. And, well, that's also what we did in part 3. We kind of simplified it, right? We brought the m in. So if you bring the m in, then you have the square root of m kx squared. So there's your momentum as it hits the wall. Now, what happens when it hits the wall? Well, that's where that changed momentum comes into play, right? Because this momentum is how much it had coming into the wall, but there's this force applied on it for a certain time, and that's actually going to change it. So if you imagine this thing hitting the wall, it's coming in like this, and it's bouncing off and going out in the other direction. So the change momentum, if it had this much momentum, just whatever number this would be if you plug numbers in, the change in momentum would be this number minus or the final momentum anyways, would be this number minus the change in momentum, because the change in momentum is trying to make it go back the other way. So the change in momentum from the wall, is equal to 25 F delta T. That's what we had from part 4. And so here we have the final momentum being the initial momentum, I guess we'll write that out, initial momentum minus the change momentum. So the initial momentum is mkx squared minus the change in momentum, 25 F delta T, and that's going to give us our final momentum, which is going to be mv prime. Okay, this has probably already started to get you confused, but think about it though. We had initial momentum, mv, we just plugged in the v, and we had this change momentum, which was 25 ft, so the change momentum is taking away the momentum. We're actually trying to change in the other direction. So we have the initial momentum, this thing, minus that change right there, and that's equal to our final momentum. And so if we want the velocity as it hits or bounces off the wall, I can divide all this by m. And so I have the square root of mkx squared minus 25 ft delta t, all that divided by m, and that should give us v prime. Now that's not very pretty. I agree with you, that doesn't look pretty, but that's kind of what we got. Hopefully I'm right. Alright, so we'll take that. Answer the following using clear, coherent sentences. Describe the significance of the time 5t on the force versus time graph. So over here, what is the significance of 5t? And I'm not going to write anything down, I'm just going to talk to you. It's going to be your job to write. Clear sentences. You guys that write in very, very light pencil writing, stop it. Find you guys. I'm going to give you guys a pen. I'll give you a paintbrush so you can't write lightly. Anyways, 5T. So this ball comes in. Imagine what's happening with this ball. This ball comes in and it hits the wall and it starts to squish down. It starts to get slowed down by the wall and it starts to bounce back in the other direction. So what 5T is representing is that's where the ball is the most squished into the wall it can get. If you take a jump off of a table and you land on the floor, your legs will flex a little bit. And so here they are, you're landing on the floor, they're flexing, and then you get to push off in the other direction, but you're not pushing off with as much force there. There's going to be this maximum amount of force because that's the midpoint of your collision. So the significance of 5T is that that's right in the middle of where this ball has stopped. This ball is moving, it's going to hit this wall, and the wall needs to slow it down. And as it's slowing it down, there's this point where the acceleration, the force is the greatest. And then it gets to bounce off in the other direction, and the force gets lesser and lesser and lesser. So 5T, the significance of that is that that's where the ball is turning around. That's where the ball has zero velocity, and yet it has maximum acceleration. Because if it's a ball, it's probably going to squish down a little bit, kind of like a spring. And so at that point right there, that's where the spring is the most compressed. That's where this ball is the most compressed because it's hitting that wall and then it's going to bounce off. So that's where 5T is significant. The last part, 6. Identify and describe what changes, if any, would occur if the assumption that the ball maintained only a constant horizontal velocity were not made. So in the beginning we said, hey, this ball comes out of the gun, it only stays at a horizontal. So it goes like this. Here's the ball. It stays at a horizontal, and it hits the wall, and it bounces back the other way. But what we're saying now is, what if we didn't assume that it had constant horizontal velocity? What if gravity actually came into play here? And if gravity came into play, then this ball, as it moved to the right, would also start to move down, and then impact the wall like so. And if it hits the wall like so, well, what happens? It's going to bounce off like so. Okay? So in this case, it goes in, bounces off. In this case, it goes in and bounces down in the other direction. I guess those vectors aren't necessarily the right size. But, identify and describe what changes, if any, would happen if we made this assumption, or if we didn't make that assumption. Well, we'd have to calculate for the drop of the ball. We'd have to figure out how far away the wall was. We definitely need to know this, right? And given that the change in position would give you also a change in time, we're doing some two-dimensional kinematics. We're doing some projectile motion. And so when the ball hit the wall, it has a momentum vector like this, which means that it has a vertical momentum vector. It has a horizontal momentum vector. And if it's a wall being a normal wall, the wall can only push back perpendicular to itself. So if the wall can only push back in this axis, then it can only change the momentum in this axis. It can only change this horizontal momentum. The vertical momentum doesn't change at all. The wall can't do that. Unless we consider the ball maybe taking on a spin from the friction. Friction would be able to do that, but the wall just being the wall, the normal force, wouldn't be able to do that. So we definitely need to consider that. Would have to break up momentum into its two vectors. We'd have to consider that the force now from the wall onto the ball, all this stuff is rhyming, it wouldn't be as high it was before. So a lot of things are changing here. Instead of just, we just need to consider gravity. It's the gravity is going to change the velocity's direction. And that kind of changes how you would answer this problem. Identify and describe what changes, if any, would occur. So we talked about that just now. I'm just not writing sentences down. I'm more talking to you, talking you through it. It's going to be your job to figure out how to describe that in your own words and your own understanding. All right, so that's going to be this problem. Problem number 3.